My name is Oliver, and in the next 30 minutes, I'm going to cover the troubleshooting, the act of recovering operation of systems. I'm going to rush through things a little bit because I got quite a hard time to fit everything that I need to cover in these 30 minutes. First and foremost, I'd like to give the due credit to this great book by Jason Maxham. It was published 10 years ago, but it's as current as it was back then. The thing is, he spent some time interviewing a number of professionals, from doctors, car engineers, network engineers, civil engineers, and try to extract what is the essence of troubleshooting. Not specific to any particular craft or profession, but something that goes beyond, right? The techniques and the mindset that are needed to troubleshoot in pretty much any area, rather than in that very specific one. It's 400 pages full of incredible storytelling and details, and it just got me to rework all the presentation that I have a few years back. Point being, this is the only book of its kind that I'm aware of, so where it makes sense, I stick with the terminology and the naming he's coining, right? Not to reinvent and name the same things differently. Because another thing that turned out that a lot of people are doing pretty much the same thing or using the same techniques, but they are not aware of them. They don't have a name because that's something they just picked up from older colleagues or books or maybe from some other kinds of learning, but they're not named and they are not uniformly recognized. And that's something that the book is doing, and where it makes sense, I adhere to the same naming in that. So in the presentation, I'm going to refer to a couple of mindsets that are very important for troubleshooting and recovering operation. We're going to cover some of the techniques and some of the questions I find very, very useful when troubleshooting something or helping somebody else to troubleshoot. So first, mindset. This is a distinction between expert and a fixer. This is something that the author have researched, and he found out that one of the things he researched, what makes somebody a good troubleshooter, and most popular answer was to be a subject matter expert in that given area, which is kind of obvious, right? When you have a medical problem, you go to search a doctor, not a car engineer. The thing is that in IT, oftentimes we are not fully domain experts in the particular area. We have more complex systems, more cloud providers. We are expected to understand from software development, let's say, to vendors, to execution environments. And it hasn't been like that always, right? As our IT systems are becoming more and more complex, we're spread quite thin compared to the past. So it's less likely that the next problem that hits you, it's in an area, in a library, or in a code that you wrote. So you're expected to recover operation even though even though you don't fully understand the particular component or deployment, etc. So we cannot really rely on the fact that we would be an expert where we are expected or motivated to restore the operation. That is the other mindset, and that's a mindset of a fixer. And that's to have a strong diagnosing skills that are, as I said, universal. So you can learn them in one area, but apply them in the other, right? And the domain knowledge is something that you can acquire as you go. You can learn a little bit, right, about the problem, about the technology, about the cloud vendor or operating system. And you always can learn just as much as you need to resolve today's obstacle, right? Provided you have the diagnosing skills, because they will guide you through the process of recovering the operation. So we don't necessarily need to rely on the domain expertise of an expert. So let's take a look at if we can take advantage of a bit more of a fixer mindset. So one of the first techniques that I have is compare with the one that works. I bet that this very sentence has irritated pretty much anybody that I know. It works on my computer, right? Everybody gets frustrated about this. The thing is, I like to see this as a good thing, right? Because all of a sudden, we have a specimen that is actually functional, right? Different environment, different computer, different deployment, different run. Even though, it could have been working last week, but it's not today. But still, we have something to compare it with. What has changed, right? What is different? Different versions, different configuration, different inputs, different contexts, right? And that's a great technique, comparing with a working and non-working specimen. What I like to do is taking the non-working one and try to make it closer to the other way around. Not working one and make it closer to the working one. Updating a library so they match. Changing the config so they match. And this way, narrowing down what the cost can potentially be, and at the same time, bringing them more in sync and eventually discovering what the problem might be. Very specific act of this that I like to use is textual diffing or comparing, right? You can have execution from last week that have passed and the today's that is failing. If you compare them textually, right, you need to ignore some random IDs and dates, which is the annoying part, but usually you learn that they kind of start the same, and the broken one is interrupted, usually with nothing or just an error message. You compare them, you see how the healthy, execution looks like, and usually just before it blows out with an error, there is a significant difference. Maybe something extra is done, maybe something is not done in different order or different values, etc. It is usually very, very telling what is the cause of why it have blown up later. So this is one of the techniques. If you move further, and I bet you know this one, rubber duck debugging. For those that did not, this goes back to an anecdote. The thing is that when you're trying to resolve a particular problem, you use your brain in a certain way. You're trying to fix, you're fixated on fixing the thing. If you go and ask for help, somebody else, you change how your brain is actually thinking about a problem because you're describing it. You're looking at the same thing from a different angle, which actually helps you to see it differently. And oftentimes I can go to some of you describing my problem, and before you even speak, I said, well, you know what? I got an idea. I either fix it or I make a significant progress just by getting it out, just by thinking about the problem differently. And it went that far that, somebody was given a rubber duck, like, you know what? Don't even talk to me, don't interrupt me. Have a rubber duck, speak to it, right? Because it does the thing. You switch the brain, and you don't often, sometimes you don't need the response from the other side because just switching the brain is good enough. We can move this one step further, and that's using your favorite AI assistant instead of the rubber duck. The thing is, the obvious downside of the rubber duck is that it never tells you anything of value, right? If you have AI assistant, it sometimes tells you something of value, right? It still switches your brain into the different mode, right? You still have to articulate a problem, which is the great part. So sometimes you don't even need the answer as far as the rubber duck goes, right? But it might. As always with AI, right? Half of the reason, the content or suggestions is, junk or not applying to what you need, and the rest need to be taken with a grain of salt, of course, right? But it can still provide you a valuable insight that you can find beneficial with your further troubleshooting. So do not shy away from using our AI assistant, not to go and fix this or tell me how to fix this, but just to get things out, ask for suggestions and possibilities. So I will have some more AI tips when I found AI assistant to be very, very valuable in what you do. Another piece of the mindset that is very important, right? Same as with physical tools or, programming libraries or knowledge of technologies, the troubleshooter's toolbox is still a set of tools, a set of way of looking at things, and set of techniques. Obviously, if you have few of them, you're somewhat limited into what you can find, what you can resolve, where you can recover the operation. The more techniques you know, the more competent you are, and the more likely you are to fix the next problem, and of course, the easier it will be for you to fix it. So think of it like this as accumulating a new techniques that you need. Another, and it's a very important piece of the mindset, is the economics. The thing is that recovering the operation is not only, intellectual exercise. It's not about fixing somehow or figuring out what the problem is, right? But you also need to do it fast. You also need to do it cheap. And I don't mean let's cut the corners today and let somebody else to handle it later. I mean, in total, right, have a fix that is the most economic one. Because there's usually a number of ways how to solve a problem, and there's usually a number of ways how to get to the bottom of what the problem is. And you obviously want to be able to select the ones that are one of the cheapest, one of the fastest. And that's exactly where the packed tool belt is going to help you. Because when you only have a few techniques, they might not be very efficient for your today's problem. If you have more, it's easier for you to choose the other one that might be actually more efficient to resolve what you're looking at the moment. Another thing there is, some problems are not worth fixing at all, right? I stole this formula from the book, and it's essentially when the price to tolerate a problem or live without the value it was giving is actually higher than the price to fix it, and it makes no sense, right? So living without a service, tool, device may actually be easier and even beneficial compared to actually trying to fix it. Which brings us to another technique, and that's verifying the inputs and the outputs. Oftentimes when you work with either devices, might be components, computer programs, we usually or generally don't have an insight how they work internally, right? And we can see them as a black box that is essentially being fed some inputs, user stimulus, files, whatever, right? And producing some kinds of outputs. If we do this, we need to be sure that we understand it correctly, that how we're using it, and what is a reasonable expectation of what it does in the end. If some of this is wrong, we might be actually troubleshooting why the device is behaving incorrectly somewhere inside, but what is actually wrong is our understanding what it's supposed to do to begin with, right? This is a definition I would bet that I picked up somewhere, but I cannot find it out, but I cannot quite claim it as my own, so it's without a source, but I like it, right? Because it exactly depicts the fact that our expectations and our observations can be wrong as well. Another technique, and this is a very essential one, that's inserting a probe. Usually, when we get back to the black box concept, we don't know what's happening inside of a device or a library or a component, right? But we need to examine it somehow. One of the ways is obviously learning how it works internally, but usually we need to examine what's going on. And probes are different kinds of way how to figure out what's happening inside. It can be a measurement. It can be reading a temperature. It can be just discovering if some parts inside is being executed or not. Some of these are very essential. Logging, verbose output. If you think of it, all these are probes that was put into, let's say, a computer program by their author. You can activate them, you can ignore them, right? But at any single point they tell you, the execution reached here and with such and such state. That's what logging is, right? Interactive debugging is somewhat of a different beast, right? You essentially stop the execution and you have an opportunity to look around. You're not looking for a particular value as from a log file, but you can choose to check number of things and then think of further things to check based on what you have found now. This is fairly essential. One of my favorite kind of probe is induced breakage. What you do, and usually you do this when there's no enough logging, you cannot easily debug or stop it or look around. It's using a component or a program or a service in a way that you know is not going to work, but it's going to blow up or error out with the way that you expect. You feed it incorrect inputs or environment on the purpose and see if it fails and how it fails, right? This is a great way to verify if the execution reached the point that you hope. If you get it to fail at that point, well, you know it did reach the execution. Or you can verify if some of the inputs are correct. You make them incorrect on a purpose and see if it blows out. And then that will verify that it was correct originally. Another important piece of the troubleshooter's mindset is that there is no sure fix. Pretty much every fix is an attempted fix. I mean, for a very simple problems and for very experienced troubleshooters, you might be close to certain how to fix things, right? But usually you just attempt to fix it, and then you verify, of course, right? If you were right, you verify it, then you just polish it, document properly, commit things, etc. You're done, you have successfully fixed things. But when it doesn't work, the attempted fix doesn't work, you got to revert, right? And that's why it's very important to touch one thing only. If you do a number of changes, it can be very hard to remember. What are all these things that I need to revert? What did I did, in the past half a day? Hard to remember, right? So if you only change one thing and one thing only, it's a whole lot easier to revert them just in case the attempted fix wouldn't work. Another reason, and this is even more important to touch one thing only, is that you don't learn what exactly worked. Usually, you don't need to tweak 15 things in order to fix things. Usually few, and usually one. If you do 4 or 5 changes, you don't really learn which of them was necessary. And you always risk that some of those changes that was not necessary will have some undesired effects somewhere when you're not looking, right? So if you minimize the number of things that you change, either for troubleshooting or fixing, you're going to reduce the amount of potential problems that you insert, right? So there's no do. Just try and then verify. And this is a pro question that I like to ask. Sometimes myself, but usually when I work with somebody else, especially when there is somebody who is approaching me from a customer perspective. And that's if the thing, device, or workflow or use case worked before. This is very important because if it did work before, it tells you that it's even possible to fix it. Some things are not, or maybe it's just not worth it, or I'm not able, or my team is not able, right? If I know it did work, this is a very important thing for me, that it's even worth trying, because it's provably something that can be done. That's one thing. And another thing, it actually sets your expectations. As I said before, there is no sure fix, right? And the question is, what to expect when you attempt the fix? Do you expect things to just start working entirely? Or maybe you just improve it a little bit, but you're still in a situation that is still somewhat broken. So, and this is an important distinction. For the pretty much devices and services that used to work before without many changes or recently, there's usually very few things that went wrong, very few config changes that was introduced, very few things that could have broken in between. So usually when you fix some or attempt the fix, it's reasonable to expect that the operation will recover pretty much fully, right? Because there is very few things that is wrong. If it does not recover, you're very likely applying a fix that is not efficient. On the other hand, if whatever you're troubleshooting did not work before, usually don't expect there will be one obstacle. More likely you go from broken, somewhat working, and somewhere in the end you get a thing to work, right? So when you're working or troubleshooting a particular obstacle, you don't expect to jump at the very end immediately, right? You somewhat expect that there will be a further process, right? So in that case, when you attempt the fix, you don't expect things to turn green immediately. You usually expect that you would get somewhat further, but not necessarily to the full recovery. And that is very important to discover what the pipeline, so-called pipeline is. If you think of the black box concept and learning how components or devices are actually working internally, you discover that there is pretty much a pipeline connecting the inputs with the outputs. The pipeline might necessarily be linear, but pretty much just a transformation. One process of acquiring the domain knowledge is discovering what the pipeline is and how it actually turns the inputs into the outputs. That's why, and these guys are necessarily chillful, because different error doesn't necessarily mean progress, right? You essentially want your execution to progress further and be correct at the entire time. So serving a different error for a different reason might actually, be a symptom that you have broken things even more because they fail even sooner or at the same place for a different reason. What you want to know is how the sequence is actually working internally and making sure that the error and the further obstacle that you're running into is actually, further down the road, and therefore you are making a progress and not, standing on the same place or even worse, moving backwards. That's the situation in case there's multiple problems and not just one. If you think of it, you can really apply a bisecting to the problem area in the pipeline. You usually insert a probe, ideally somewhere in the middle, right? And you see, have the execution reached here? Great. This part probably works well, so the problem must be in the other half. On the other hand, if it does not, we know that the problem is in the first half, etc. Of course, this all depends if we can know how to insert a probe there, if we can observe the information from that, etc. But this is a great way how to narrow down the problem into part of the pipeline and dive deeper in identifying where the problem can be. Another very, very important technique, and that's separating facts from assumptions. Oftentimes, we have our belief how things are supposed to work, right? And honestly, sometimes it's incorrect. That's why it's important to keep what we have measured. What is the error message exactly, right? This is a very infamously thing done wrong. What is the exact reading? What is the exact value that we observe in the correct working or incorrect one? And usually every assumption needs to be verified. You see, when you look at maybe a computer program or a deployment, usually it was put that way by somebody or a team, right? So apparently there is someone who assumes it's supposed to work like this. But the very fact that you're troubleshooting means that it's not. Some of the assumptions, somebody's assumptions must be wrong, right? So don't trust them, always verify and replace them with facts. This is a great thing. You can ask your AI assistant, how do I verify something is like this, right? Usually they give you a number of suggestions, right? Half of them cannot apply, it's not sufficient, or you cannot apply them for some other reason, but usually it's a great way to discover the blind spots and, I haven't thought of this, or whoa, I can be figuring this out in this way. It's very, very good source of some approaches that you haven't thought of so far. If we move further, there is a bit of another piece of the mindset, and that's something I call a set of possible causes. Let's presume that you have collected your facts, your symptoms, right? And in theory, there can be a number of causes. You don't know them all. You cannot list them. You try, it would still be a waste of time, right? Because there's a number of situations that you don't even know would manifest this way. But fortunately, we don't need this, right? And And oftentimes I run into people that say, well, I have a theory and now I'm working on proving or disproving it. Having a theory essentially means from the old set, I'm feeling lucky. I believe that this is the cause. And now I go and I try to prove it. If I'm lucky, great, right? I have nailed it on a first try, very impressive. But if I don't, I have a set, and from that set of mostly unknown causes, I have eliminated one item. That's not very efficient progress if you think of it, right? Usually, it's a whole lot better to collect facts and symptoms. And this is even easier when we have a number of theories, right? Because we can look at two possible causes that we can think of, and we can design pretty much a scientific experiment and see what would be different. If this is the situation or that is the situation, what observation would be different? Where to insert the probe to tell, is it this or that? And remember, we are not proving or disproving individual theories, but we are collecting valuable facts. And with that, I can simply go, verify, and cut half of the set away, simply because the fact disproves half of the theories. And those are theories I haven't even thought of. Maybe nobody in the team could think of it, maybe we don't even know it can be broken, right? But we have just eliminated it by collecting that particular fact. Going like this, iteratively, we can go and narrow down the set further and further until there is something, there is very few possible explanations, or we simply are lucky and guess that. And this is probably where AI agents can be the most useful, and that's asking them to suggest possible theories. And that's why it's so important to collect the facts and symptoms, because you can simply take them, slam it into your AI agent, and ask it to provide different explanations for this, right? Again, half of it will contradict the symptoms, right, or not be very useful or duplicated, etc., but easily it can point out the blind spot of things that you haven't thought of. This is something I consider very, very important. Another pro question, it goes back to something that is known as XY problem, and it's something I like asking, what are you trying to achieve? That's usually when I'm trying to help to somebody else. I'm sure that you stumbled upon this. So there is a colleague, friend, customer coming to you with a problem. You work on this, you successfully resolve that. They get a solution, and they get back saying, it didn't help me. You see, yeah, we fixed this thing, but the only reason I did this was to fix this other thing I haven't told you about, and it doesn't work for that. This is happening, and usually technical or engineers are very prone of this, because they run into a first problem and they try to help themselves, right? Of course, right? They try to fix it on their own. They suggest the path how to resolve or work around their first problem, and they stumble upon the problem why. And they only approach you with this one. So asking people what they're trying to achieve is asking them or forcing them to step back and say, well, yeah, I'm actually stuck on this thing, and the only reason I'm doing it to resolve this very problem. And that other problem can have much more straightforward solution. Maybe it's just documented, maybe it's something that you might know that there is no solution for, or no approved solution, etc. So this is usually very important, and it saves time on both ends. What are you trying to achieve? If it's not this case, it definitely helps you to understand what the context is, right? Why the person needs this and how important that is. And you can actually, weigh in how much time, effort, and priority to dedicate to this. I guess this is the last technique that I have here, and that's somewhat bordering with the mindset, and it's peeling the onion. You can think of it really like an onion when the end-level use case is at the surface, and the root cause that prevents it from working is in the very inside of an onion, right? And as you troubleshoot, you keep on opening all these black boxes, and you're diving deeper and deeper, one layer after another. A lot of the people, and it's this very, very engineering thing, we see this as a hunt, right? We find the root cause and discover it and then fix it and eradicate it at the core, right? But oftentimes this is not needed. Sometimes we cannot even do this, right? Maybe this is in a library that we don't control, right? Maybe in a computer program that is long unmaintained, or maybe this is an external vendor and we cannot get them to fix the bug. That would be the root cause, right? But we simply cannot address it. But there are other things, right? Well, why I use the analogy with the onion is that we can compensate at every single level, right? We mentioned that when something is not worth fixing, we can just take it and throw it away. That would be throwing away the entire onion, right? We leave the use case unsatisfied. Other approach we can take is practically compensating. Maybe at one of the inner layers, not like the innermost, but some of the inner layers, we change the inputs. We change the output. That's a workaround, right? We change how the component that we cannot fix is actually interpreted by its surrounding. Another thing we can do is we can take some of the inner layers and replace them entirely. You wouldn't think of troubleshooting why a light bulb stopped working or try to fix it. You just take it, and there's some of the few inner cores, throw it away, and replace it with a new one. So this is something that we must keep in mind, simply that the root cause is not something that we need to discover and resolve. The great thing about this is that oftentimes it's easier and cheaper, both to fix and to troubleshoot. Because, diving deeper and deeper and deeper has its cost in money, maybe you're asking a vendor for help, your own time, etc., right? So if you can eliminate some of this, both the fixing and the troubleshooting, you can save a lot of resources that way. And I was faster than I expected. Thank you very much for your kind attention. We have more times for questions than I hope, and I wish you happy fixing.
Yeah, I have mostly not a question. Oh, it's working? Okay. So it's more like update maybe for what you said. It's most important thing is with the process itself, it's also like to set the points, what the minimal expectations will be from your side and from the customer. Because that's also help you to keep you on that comfort zone. Because when the problem starts, you're getting out from your comfort zone, you're under stress. Mm-hmm. And actually what it's helped in this way, you set the levels, what you expect from the service at minimal. So like SLAs. Mm-hmm. And if you set that, that actually allows you to be focused on the problem, because if you achieve that level, let's say, if something doesn't work, but you can always say like, oh, if the previous version worked, can you roll back to the previous version? And if the customer said yes, then you back to your comfort zone, because then you can sit back and start actually debugging. Mm-hmm. Because otherwise, you'll be under pressure, because you have to fix it. And right now, like fix is something we don't know, but if you have those levels, that actually allows you to be more comfortable with the problem. Mm-hmm. So yeah, I think it's also quite important.
That's an interesting point on a process side of things, right? The recovery doesn't necessarily need to be full if this is okay with you and the contract and the customer, etc., which goes back to the economics, right? You don't necessarily need 100% fix or 100% restoration, or maybe you don't need it immediately, right, on a Friday night, right? So yeah, that's a good point.
So I have a question about the comparing the working and non-working systems. So I have one note and one question. So yeah, you mentioned the text diffing, which is, I think that's what works for me as well. What I found very useful is collecting all the data that I can get on the systems. For example, for RHEL, it's SOS reports, and you can compare the directories, right? So we were dealing with performance regression or issue, and it turned out to be a sysctl change, right? So, so that's one thing that's my note, like a recommendation. Just curious, do you have some other tools that you use for diffing the systems?
Like the entire operating systems or directory structures?
What do you use? You mentioned text diff, but I think it's more than that.
That's the simple case, right? When you have two files, it gets more complex with the number of them. Depending. So you're looking for more efficient diffing or something that will just extract the most important information? Because for me, that's the more challenging part, right? Figuring out what can be relevant. What are all the things that can differ, and it can be significant. So that requires the domain expertise, right? If I, let's say, never work with Linux, it will be very hard for me to figuring this out, but I can have the skills and tools and whatever to do the comparison, right? So yeah, that might require acquiring the needed domain knowledge. I try to deliberately not to go into the particular tools at systems, partially because that would expand to the entire day, not 30 minutes. So I keep that out on a purpose. That's one thing. And another one is that it's always specific to the given environment, right? I mean, there may be software developers interested in some part, but it would not be so much interesting for DevOps engineers, right? So this is very specific to what you do and very environment.
Yeah. So I have a more generic question about the comparing working and non-working systems. So you mentioned that you tried to use the working system and do changes on that system to get it not working.
I misspoke, the other way around, right? Because the other way around. Sometimes you have to resort to this, right? But usually it's not what you want,
yeah,
right?
Because I see the risk that you would make the working system into a state where you can get it working anymore.
Usually you want to take the non-working environment and make it closer to the working, up to the point that it's working as well. But sometimes this can be, let's say, expensive or time expensive, right, to do this. Maybe, I don't know, I won't make an example, right? Sometimes it might be actually easier to try to temporarily break the working one. Let's try to use the same version as the not working and see if it starts failing and if it starts failing in the same way. In that case, we have took the right constellation that was working fully, and we make one single change that has reliably broke it in the same way. And we practically just found out that that is the cause, right? And then if we know how to fix this, we know that this is the right path, and we can decide if we want to invest into fixing the broken system in this particular way. Before verifying this in the working environment, it would be an attempted fix, which can actually turn into an investment that never returns. So yeah, there are rare cases for this as well, but no, it was a mistake on my side.
Thanks. What would you say is the first question you should ask when someone comes to you and says, hey, this isn't working?
For me, it's definitely one of these pro questions are those that I ask typically, right? Have it worked before, right? That's one of the things. And what are you trying to achieve in the end? Because, as I said, oftentimes there might be a prepared resolution to this, right? Existing customer cases or just documented workaround, etc. But when we don't, because different people describe pretty much the same problem differently, right? And when you perceive this, you don't get, capture the entire concept. So if you get them to speak a little bit, you better gauge how important this is, if they really need this, if they have a workaround, etc. Right? So these, I call them pro questions, but usually I ask them very, very early in the troubleshooting process, right? Simply because the earlier you ask them, the more time and effort they can save you entirely, right? If you debug for a half a day and then you ask them, it still helps you, right? But the half of day was already invested.
Thanks. I would say it's when did it break?
Sorry?
When did it break?
When did it break? Of course, right? As I said, when I was starting with this, I got 45 minutes and I was not able to make it any faster. So I'm actually surprised I get it below 30. Yeah, I mean, when we get back to the situation that you mentioned, usually when things worked before and broke, you look into how much time have passed and how many changes have been introduced into the system, right? Obviously, one of those changes is very likely the usual suspects that did cause the error. Sometimes you do know what the changes were. Sometimes you are not even aware of the change, and that's why you're troubleshooting, etc. But yeah, if you get to the bottom of when it worked, when it did not, and what have changed, you have narrowed down the problem fairly significantly.
So you've read the book and then you kind of decided to start using this methodology. What was most difficult part to take it in the real life? Or was there any difficulty starting to use this methodology?
Right. Somewhat of a long answer. This book have make a significant emphasis on that there is not a methodology, a step-by-step process, etc. No one have identified such, right? And not even in any of these individual professions exist a particular methodology that will go step by step. That's why we talk really about a tool belt. You still need to use your ingenuity, right? Figuring out which way to use, which approach to use, which troubleshooting technique to use, right? And if you get two people to troubleshoot the same problem, as you surely know, they do it in a vastly different time, right? Because somebody is using a different technique, which turns out to be more efficient than the other, right? So rather than a methodology or a process, it's really a number of tools that you're using, and obviously it's an experience of a troubleshooter to choose the right one, know the right one, use them effectively, and be able to switch them. That's actually an important thing, right? When you try to resolve or troubleshooting in a particular way, it can take days, hours, and you can be fixated on that. But there can be a different way how to find it in 15 minutes. But if you keep on focus on this one, so usually when I get annoyed or frustrated, I step back and try some of the other techniques, right? So yeah, given that we are out of time, I will consider this to be the most important part.
Thanks.
Thank you.